Standing approximately 120 meters tall when fully stacked, SpaceX's Starship is not just the largest rocket ever built. It represents a fundamental reimagining of how we access space. While rockets have historically been treated as expensive, expendable hardware comparable to building a 747 for a single flight and crashing it into the ocean, Starship's design philosophy borrows from aviation. Build it once, fly it thousands of times, and refuel it between flights. If this vision succeeds, and the engineering challenges are formidable, it won't merely improve space travel. It will break the economic equation that has constrained humanity to low Earth orbit for half a century. The revolution isn't in reaching space. We've been doing that since 1957. The revolution is in the cost, frequency, and scale at which we can do it. Here's why Starship, if it achieves even a fraction of its design goals, will fundamentally transform what is possible beyond Earth. The economics of full reusability. To understand Starship's potential impact, you must first understand the brutal economics of traditional spaceflight. A modern expendable rocket like NASA's Space Launch System, SLS, costs roughly $2 billion per launch. Even SpaceX's workhorse Falcon 9, which pioneered first-stage reusability, costs approximately $67 million per launch in its expendable configuration. The propellant, the rocket fuel, accounts for less than 1% of these costs. The overwhelming expense is the hardware. Engines, avionics, structures, all destroyed or abandoned after a single use. Starship is designed for full and rapid reusability. Both the Super Heavy booster, the first stage, and the Starship upper stage are designed to return to the launch site, land vertically, be inspected, refueled, and fly again, potentially within hours or days. SpaceX's stated goal is airline-like operations. The propellant cost for a Starship launch is estimated at less than $1 million, primarily liquid methane and liquid oxygen. If the vehicle can be reused dozens or hundreds of times with minimal refurbishment, the per-launch cost could theoretically drop to a few $1,000,000. This isn't speculative fantasy, it's basic arithmetic. The engineering challenge is building hardware robust enough to endure repeated launches and landings. SpaceX's Falcon 9 boosters have already demonstrated reusability, with some flying more than 20 times. Starship aims to push this further by making the upper stage reusable as well, something no orbital rocket has ever achieved. A cost reduction from $67 million to, say, $10 million per launch doesn't just make space 6.7 times cheaper, it changes the entire calculus of what missions are financially viable. Projects that were impossible become routine. The payload revolution. 100+ tons to orbit. Current heavy-lift rockets can carry between 20 to 30 tons to low Earth orbit, LEO. NASA's SLS can lift around 95 tons, but at $2 billion per launch, it flies rarely. Starship, in its fully reusable configuration, is designed to carry approximately 100 to 150 tons to LEO and do it frequently and affordably. This capacity alone rewrites the constraints of spacecraft design. For decades, engineers have been forced to design satellites and space probes that are as light as possible. Every kilogram costs tens of thousands of dollars to launch. This drives the use of exotic, expensive materials, miniaturized components, and years-long integration schedules. The James Webb Space Telescope, for example, weighed about 6,200 kilos and cost $10 billion, partly because it had to be folded into an impossibly complex origami to fit inside a rocket fairing, and partly because failure was unthinkable given the expense of launch. With Starship's capacity and low cost, the paradigm flips. Engineers could build heavier, simpler, more robust spacecraft using cheaper materials. Redundancy becomes affordable. Instead of one $10 billion telescope, you could launch 10 smaller, cheaper ones for the same price, or less, gaining redundancy and broader coverage. The risk calculus changes entirely. Large space stations, huge telescopes, interplanetary ships assembled in orbit, propellant depots, all become feasible when you can affordably lift hundreds of tons. The methane advantage, fuel for Mars and beyond. SpaceX chose liquid methane, CH4, and liquid oxygen, LOX, as Starship's propellants, a departure from the RP-1 kerosene used in Falcon 9. This decision is critical for long-duration missions and in-situ resource utilization, ISRU. Methane burns cleaner than kerosene, leaving less residue and reducing engine maintenance between flights, essential for rapid reusability. More importantly, methane can be synthesized on Mars. The Martian atmosphere is 95% carbon dioxide, CO2, and water ice exists beneath the surface. Through a chemical process called the Sabatier reaction, CO2 plus 4H2, CH4 plus 2H2O, methane and water can be produced. Electrolysis then splits water into hydrogen and oxygen, providing the oxidizer. This means a Starship could land on Mars with empty tanks, synthesize propellant from local resources, and return to Earth, without needing to carry all the return fuel from Earth. The mass savings are astronomical, making round-trip Mars missions not only possible but practical. No other operational rocket is designed with this capability. In-orbit refueling. Unlocking the solar system. Even with its massive payload capacity, Starship cannot reach the Moon or Mars with a full payload in a single launch from Earth. Rocket propulsion is limited by the tyranny of the rocket equation, the need to carry fuel to lift fuel, exponentially increasing mass. Starship's solution is in-orbit refueling. The concept is straightforward. Launch a Starship into orbit, then launch multiple tanker Starships filled with propellant, transfer the fuel in orbit, and send the now fully fueled Starship on to its destination. NASA analysis suggests that a lunar mission might require 8 to 16 refueling launches. A Mars mission could require more. This has never been done at this scale, and the engineering challenges, transferring cryogenic propellants in microgravity, managing boil-off, docking precisely, are significant. But the physics is sound, and SpaceX is developing the technology. NASA has already contracted Starship as the lunar lander for the Artemis 3rd mission, contingent on successful demonstration of orbital refueling. If orbital refueling works, it eliminates the mass constraints that have bottlenecked deep space exploration. Suddenly, missions to the outer planets, asteroid mining operations, and crewed Mars expeditions transition from science fiction to engineering problems. Rapid iteration. Failing. Forward. Traditional aerospace development is slow and conservative. Rockets are tested exhaustively on the ground, then once in flight, and failure is catastrophic, both literally and financially. The SLS took more than a decade and $20+ billion to develop. SpaceX uses a radically different approach: rapid iterative development. They build prototypes quickly and cheaply. Starship is made of stainless steel, far cheaper than advanced composites. Test them to failure, learn, and iterate. Early Starship prototypes exploded spectacularly on landing. Later versions flew higher and landed successfully until they didn't. Each failure provided data. This approach is only viable when the cost of failure is acceptable. Because Starship is designed to be cheap to produce and reusable, SpaceX can afford to lose vehicles during testing. As of late 2024, Starship has conducted multiple integrated flight tests, progressively achieving more objectives: stage separation, controlled re-entry, booster catch attempts using the launch tower's chopstick arms, and engine relights in space. This iterative method accelerates learning. Where traditional programs might take 15 years to develop, test, and fly, SpaceX aims to do it in a handful of years through dozens of test flights. The implications: a new space age. If Starship achieves full, rapid reusability with 100+ ton payloads at costs orders of magnitude below current systems, the implications cascade across every domain of space activity. Science. larger, cheaper telescopes and planetary missions become routine. We could send dozens of probes to the ice moons of Jupiter and Saturn, searching for life. Commerce. Satellite internet constellations could expand massively. Space-based solar power, long dismissed as uneconomical, becomes plausible. Asteroid mining transitions from speculation to business case. Human presence. Large, comfortable space stations. Lunar bases with frequent resupply. A sustained human presence on Mars within our lifetimes. The key word is if. Starship is still in development. Orbital refueling is unproven at scale. Re-entry heating, engine reliability, and countless other challenges remain. But the engineering is rooted in physics, not fantasy. SpaceX has already revolutionized spaceflight with Falcon 9's reusability. Starship is the next logical step. Whether it takes 5 years or 15, whether it's SpaceX or a competitor who ultimately succeeds, the principle is sound. Fully reusable, high-capacity launch systems will break the cost barrier that has imprisoned humanity in low Earth orbit. And when that barrier falls, the solar system opens.